All right, to help minimize some anxiety about our assessments in class, what I try to do is to give you some example problems to look at, show you how I would solve them, and it would give you a sense of the types of problems you're going to see. So for our very first learning objective, it says I can use the mathematical and graphical relationships between position, velocity, and acceleration to analyze the motion of an object. So in this particular problem, this assessment question, we're given a mathematical expression for the position of a car that's going in a straight line, it's traveling along the x-axis, and how that motion or that position depends on time. The first thing we're asked to find is the displacement and average velocity of the car between time equals 1 second and 3 seconds. So in order to do that, those two calculations, we're going to need to find the position of the object at 1 second and then also the position at 3 seconds. So if we put in t equals 1 for our time in the first position, we have 4 times 1 cubed minus 6 times 1. That gives us 4 minus 6. And so we find that it actually has a negative position. That's fine. That's just where it is. And if we do the second one, we have 4. Now this time our 3 is our time squared minus 6 times 3. So we've just substituted in the time that we're interested in for t in our expression. So we have 4 times, this is cubed. So this is 4 times 27 minus 18. And if we do that calculation, it turns out that that position is 90 meters. So the first thing we can do is find our displacement, which is the position that it was at 3 seconds minus the position it was at 1 second. So that is 90 minus a minus 2. And so that gives us 92 meters. So our displacement over that time interval was 92 meters. The average velocity uses this displacement in order to be calculated. We take that displacement over that time interval. So that's 92 meters over 3 minus 1, which is 2. So this gives us 46 meters per second. So the average velocity over that time interval was 46 meters per second. It had a displacement over that time interval of 92 meters. So those are our two answers. Then it asks what the instantaneous velocity of the car is at t equals 2 seconds. So we looked at the velocity over a period of time, but now we want to know it at a particular time. So we have to first find the instantaneous velocity, which is found by taking the derivative of the position with respect to time. So using our rules for a polynomial, we would have the power of t, 3 times 4, and then t decreases its power by 1, so it's t squared, and then do the same thing and we get a minus 6. So our expression for our velocity is 12t squared minus 6. We can put in t equals 2 to find the answer to the question that they're asked, because they want to know what is the velocity at 2 seconds. We get 12 minus 2 squared, times 2 squared minus 6. And so that means 48 minus 6, and that's 42 meters per second. So that was the velocity in the middle of the interval. It's not the same as the average velocity, and this is something that we encountered in class and in some of your other problems. When you have an object that has some sort of acceleration, you don't expect the average velocity and the instantaneous velocity to match up. That's the whole point of an acceleration. The third part of this problem asks, what time does the car turn around? Well, it turns around when the velocity is equal to 0. Keep in mind that if it has a positive velocity, then goes to 0 and then becomes a negative velocity, that's changing direction. And so we know the instant that the velocity is 0 is when it changes the direction. So we already have the expression for the velocity as a function of time from part B. And we want to set this equal to 0 and figure out when is that going to happen. So I get 12t squared equals 6. T squared is equal to a half, and so t is the square root of a half, which is 0.707 seconds. So that's when it turns around. Finally, the very last part of this problem is the expression for the acceleration. The acceleration as a function of time is the derivative of velocity with respect to time. And so we take the derivative of this expression, so we would get 2 times 12 times t, and then the derivative of 6, because it's a constant, is 0. So that's just our acceleration. It's 24t, and that's in meters per second squared. Notice that this is not constant because it depends on time, and we should have expected that, because up here we had a position that followed t cubed. And by now, hopefully you're comfortable with the idea that the position expression, when you have constant acceleration, is has the highest power for time is t squared. So like 1/2 at squared. Now I want to say two things about this example. I did make it a little bit longer because there were a couple different things I wanted to sort of show as an example of how to do it. And the other thing is that we noticed that there's also the possibility that you could be asked to work with graphs. This particular problem didn't have graph-based questions, but that would be another possibility. I hope this helps.